let's go ahead and get started. I'll record this one. Very quick recap. Okay, so last time, so we're talking about let me make sure the screen sharing is enabled. All right. So last time, yeah, we were talking about deep learning, which is based on the neural networks. And then I particularly told you that the difference between neural networks and the scikit-learn or traditional machine model is that the traditional machine learning models, we're trying to define the columns, the field, the input and outputs by ourselves. Where the neural networks trying to simulate how the brain works, the structure, and then try to pick up all these features by itself. However, as we specify the deep learning and neural networks, we still need to specify the layers, some of the configurations, and parameters. Okay. And then as we use the neural networks, there are two primary networks people did 10, 15 years ago. And CNN, I look at some of the references, I think it became really popular around 2012, 2013, about 10 years ago. Okay, so it was primarily used in the image recognition, object recognition, that type of applications. And then we also have the RNN model that handles the text, sequential data a lot better. So we'll look at that one briefly. Yeah, but obviously as you look at the structure of all of this, the whole process is more complicated than the traditional machine learning model, where are mostly based on the mathematical model, statistics models, where this one, obviously we can't even see exactly how the layers will work. We can only understand the high level. So training all of this requires more data and also takes more time and resources. Okay, so first of all, today I want to dive into a little bit more on the RNN model, because the RNN model, if you remember, it was based on the sequential model. A lot of times the RNN model was actually used to predict the sequence next word, or it's a time-based type of uh, scenarios. Okay, so that's where this has been used, and time series like a stock, financial data. You can also see a lot of RNN model being used. Okay, um, so again, to visualize this one, these two images, I really want you to remember it. So this on the left-hand side, that is how the neural networks looks like, right? So remember last time we saw some animations, you got some input that's going to trigger some of the layers here, and that's going to trigger the other layers based on which layer is being triggered here, and then you trigger more. Eventually, you got your results. Okay. However, this is a high level structure, but for RNN model, what you really want to understand is on the right-hand side. Okay. So if you look at every single step, okay, so what's really happening here is that as you're trying to predict the next one, now you got to provide the input, which is the current data or current word. And also you want to provide the previous one, which is coming from the previous layer. That's why this image here shows the fundamental idea. So let's say I want to predict what the next word going to be. So I need to give you the current word, which is represented by this x, t times 1, t minus 1. And then you also need to tell me what's the result you got from the previous prediction. So that input here is coming from the previous layer. That output plus the current one, that's going to produce the next one. And then with that result plus the next one, you can predict the next one. So that process is very similar to the rock, paper, scissors example. Okay. So every single step is closely dependent on the previous step. So that's the core idea of RNN model. But the difference is that, for the rock, paper, scissors, which is used a very simple, not very simple, but SVM model, that's the mathematical model, where this one, they form a bunch of very complicated neural networks like this. Okay, that's fundamentally different, but the idea is the same. So let's come back to this example to understand RNN a little bit better. Okay, I showed you this one last time. So the input here, you have characters and then the target, and then after the O is going to be a space. And then if you want to say, I want to predict what's going to happen after O, then you provide this input, and then we're trying to run the network to predict it. So something you need to do, you got to do some kind of very simple encoding. Here, I just gave some numbers to indicate the index, and then we want to get the results. Okay, so And again, if you think about this rock paper scissors example, that's just a five steps you saw before, and then you can use that one to predict the next one. So these are the same slides I showed last time. Okay, so I just want to highlight the idea of the sequential idea, right? So for the input here, for the first one, your letter is H, which is represented by 1. And you also need to know the result from the previous hidden layer. Think about as a networks. A lot of layers, every layer going to give you a result. So you want to look at what's happening from the previous layer. Since this is the beginning, that's going to get a 0. So as you're trying to make the prediction, your input is going to be the previous one plus the current one. You send those together in and back to that network. And then the network will give you the next results, which is the E. Okay. And then you take that E, which will be the input for this part, the previous hidden, and then the next word is E, and then if you want to predict what's going to happen after E, so you put these two together, the previous one is H, and then this one's E, and then you guess the next one, which is L. Okay, so same idea. Okay, every single word you look at the current character, and then the previous one, and then you predict the next. And then eventually you actually send it back to that network. So that's why it's called a recurrent, right? So you give input, you send it in the model, give you output, and then you bring that output back and then send it in the model again, and you do this again, again, and again. That's why it's called a recurrent. Okay, it's almost like a recursion. Okay, I think this picture I try to find a lot of things trying to explain this one, but I find this one is a lot better. So think about this input. This is upside down. Okay, so the students open there. That's the input sentence, and we want to predict what's the next one. Okay, and then what's going to happen here is that so they take the first one first, this word called the, and then you embed it, and then you send it to the neural networks and using that one of the using the hidden layer, and you're going to predict something for the next one. All right, and then what you do next is that the next word is the students. Okay, you want to combine that information from the first one and then form a layer that you can generate the output. That output combined with the next word, and then you generate the next one, and that one combine the final word, and then you can generate another thing. And then finally, you get a result. Either it's books and laptops, other things. Obviously, have different probabilities, right? So this is a kind of a what we want. Okay, so you basically, as you do the training, okay, eventually the training model is going to work like this. It takes that sentence, they break it down to different words. Every word I send it to the model, I got an output, and I use that one to combine with the next one. I can know the next one and combine the next word and get the next one. And then eventually, based on that information, we figure out what's the final results. Okay. So that process, just to clarify, this is the trained. Okay, this is the model has already been trained. That you can call it again and again and again, and then get the results, put together the next word, and then get another results until you get a final thing. Okay, so this is basically how the recurrent neural network works. Okay, so it's a very good at to process the sequential data like this. All right, a quick summary, right? So the hidden state, the hidden layer is just like a rolling memory of what's being seen. And each new input updates the memory, and the output at each step depends on both the current input and then the past. Okay, so if you think about this one and compare that with rock, paper, scissors example, it's actually very, very similar, right? So the rock, paper, scissors example, our algorithm was that, our assumption was that every of your next move is going to be based on the previous 2 or 3 moves, right? So just like here, okay, so you got an input rock, paper, rock, and then you're going to predict the next one. So that's the problem we actually showed you last week. All right. And then, but then as you running this prediction, assume you already have a model being trained, right? So you input the first one with a rock, and you give it the hidden layer first, and then it's going to generate results. And then plus that one, you add the paper, you got the next one, and that one you plus rock and then generate the next one, which is going to predict the results, which could be something like this. Okay. Just keep in mind that this is 100% dependent on the first one. and then plus the current one and give it the next one. All right. The reason I want to come back to look at this RNN model or rock paper scissors example is that these are actual motivations on why people need to build a new model. Because as you look at this process, I keep highlighting that this is a sequential model. Sequential model obviously has its advantages because it actually captures some of the sequence information, the time information, but at the same time, it's not that flexible. It's not very efficient. Because if you look at all the different papers, they will talk about, this one, you cannot parallel it. Okay. So this part actually is not that easy to understand. So that's why I want you to go back to look at this image. Because if you want to use your model to predict what's going to happen after these 4 words, what you really need to do, go back to that process I told you, is that you break them down into 4 words. You have to run the first prediction first. Throw it to the model, get a result, using that result and add these words, and then you produce the next result. That result, add this word, produce the next results, and then add this word, you produce the final results. See, you really cannot run this one until you get that one. And obviously that one is going to depend on the result of the first one. So this whole process, it must be serialized. It must be sequential. No matter how many CPUs you have, how many GPUs you have, you cannot say, okay, you do this step, I do this step. You can't because until you have the result here, you cannot run it. So that actually produces a big limitation. You cannot parallel process this one. Obviously, for the simple sentence like this, you don't feel it, but you have to always think in a large scale. Okay, assume that model is so big. Okay, taking a prediction is going to take you, hundreds of milliseconds or seconds, right? And then if you have to weigh the words one by one like this, that's not going to, show it. If you think about in the early days, the GPT-4, 3.5, the speed was actually much slower than today, right? So obviously that process matters. They are actually trying to generate the words one by one, and then attach it back and all of this. So the sequential model isn't the best fit for this type of language model processing. Okay, but once again, the ones I can show you today are very, very high level. Different one when you look at this one, you may have different understanding. So what I suggest after today is try to go back to these major steps, look at a paper, and try to understand things based on your style. Okay, use GPT heavily and try to give you a different example to help you understand. Okay, but this is one of the major limitation. The second limitation is that as you are doing this one, and the results found, okay, I cannot prove this one, but based on what we can find from the papers and everything, so this type of model tends to overweight the most recent place, and then will forget the earlier ones. I think this is actually, let's not worry too much about a theory, okay? But if you think about this from practice, it does make a lot of sense. If you think of rock, paper, scissors, okay, the strategy you can pick probably is only going to be based on the recent 2, 3, 4, 5 plays. There's no way for you to capture, even remember the ones from early days if you've played for 100 games. How does the first game matters? That's very difficult for you to actually handle. Okay, it's very hard for you to use that information. It's even harder for you to correlate those early stages with the recent ones. And also think about, you have this very complex neural networks model, and you recursively keep calling this one, get a result, keep calling this one, right? The sequential information definitely going to give you some very good predictions. But if you keep calling this for so many more times, how can you guarantee the first couple of calls still matters at the end, right? So obviously, if you think about the network, right? So the closer it is to the final stages, I think that feels matters more. Okay, but like once again, these are all like I trying to give you some kind of high level ideas and impression. If you want to dig into why that one is biased, that we gotta look into some more like proofs. But just from the intuitive perspective, okay, you can pretty much see the recent ones actually definitely matters more. So in certain cases, like rock, paper, scissors, that's maybe a good thing, right? That's how it should work. But for certain things, it's not. So for example, if you have article, okay, you got a very long article and you have a long, very long sentence, okay, something like this one. I grew up in French and blah, blah, blah. And this is why I speak fluent French, right? So in this sentence, if the last word French, okay, is the one thing that really matters, okay, if you try to predict why I speak fluent, this information from the predict correctly, you have to go back to the early ones to find out, okay, because of the French. That's probably the keyword that's going to determine the results, right? But if your model is more kind of biased or overweighted in the recent ones, then maybe that information will not be captured very correctly, and that's not going to affect this number, this final results. Okay, so that's why if you only look at the short term, the recent numbers for the language model, it may not be the most optimized way to deal with it. All right. So that's another kind of limitation based on this sequential model. All right. Another kind of a limitation you will see is something called a vanishing gradients. This is just happening in the training. I think this is kind of similar to the previous limitation. That's probably also explains why it matters more on the recent ones, because eventually you need to put as you make one prediction, okay, you have to put all the things into one like a function call. Okay, your current words, and then you put all the previous ones. But then this is recursive, right? So, and then what they do is they look at this one first and give you the results, and then they plus here, plus here, plus here. Okay, so obviously, this is going to be hit a limit, right? How many you can throw up into one function call. I don't know if you guys remember as you learn the recursion. Recursion has a lot of advantages because the code is very simple to write. If you can summarize that as a recursive model, the code is now a lot simpler. Think about the Fibonacci numbers, factorial calculation, right? But you should know the recursion is very, very heavy in terms of memory usage, right? So I don't know if you remember that if you, for example, do a factorial of let's do factorial of 8, right? So what you need to do is that you have to calculate factorial of 7, the results, and then you times 8, right? And then we don't know the factorial of 7, then you keep going to factorial of 6, okay? And then you times 7, something like this. But oh no, sorry, actually, the better example is the Fibonacci number. Okay, so if you do Fibonacci number 8, what you need is you need to get the Fibonacci 6 and then 7, right? Then you have to this one you have to calculate 5 and 4. This one have to calculate 6 and 5. But then you see the 6 here, you have to recalculate because the 6 here is already done, but here you have to redo it. Okay, so the recursive is not like efficient in terms most time in terms of memory and also the speed. The non-recursive version now is more efficient, but the recursive version is clear to understand. The code is simple and concise, right? So that's why here when you look at the RNN model, it's kind of a recursive, okay, recurrent kind of model, and you are definitely going to hit some kind of a limit in terms of how much information you can pass that one function call, right? So because of all these limitations, all right, so people found out that the language model or natural language processing need to be improved. Okay, so the most important thing, okay, right now, I really want you today to spend some time to read is this paper. This is not a very long paper, but this paper isn't going to be that easy to understand because they talk a lot of architecture. Um, in terms of technical things, once again, you don't have to understand the full thing, but try to get things out of this paper as much as you can, probably using your own example and the resources. But I want to give you some background about this paper. Okay, this paper was published in 2017 or 18. Okay, this paper was initially published in a conference. Should be the NIPS conference. Let's actually find out. So you can find the paper for free from this Cornell library. But if I remember it correctly, this paper was initially, let me see, was initially published in the uh, conference. Okay, so it should be, let me see if I can find the actual information. Yeah, so it was published in this NIPS conference in 2017. Okay, actually this one was actually on in Long Beach. I kind of let me check. Okay, there are a couple of times this conference was in Long Beach. I remember. First of all, I want you to know this conference. Okay, so this conference called a Neural Information Processing Systems. This was a long-going conference since, as you can see, 1987. In computer science, a lot of field, they have some of the major conferences, academic conferences. What people do is that you submit papers there. If you got a paper accepted, and then you will go there to present or do presentations. So all the people from this area, this research field, mostly professors, grad students, and then sometimes industry partners, they go there, they look at the results, they discuss, right? So that's what people do in the conferences. Most conference like this one has a long history. Okay, this one has since 1987. However, I will tell you this conference though obviously wasn't very famous before until all of this AI starts to develop, right? So if you look at the locations, 17 was on Long Beach, and then later on, yeah, that was the only time. Actually, this year is going to be San Diego. Okay, if you're interested, you can go. So this year, I didn't go to the conference, but I actually met one of the friend there. We actually had a lunch in Long Beach, in downtown Long Beach, and then at that time, she was telling me that, oh, the conference is so popular. Actually, honestly, at that time, the conference was already very, very popular. Okay, because self-driving everything, the CNN stuff, all already going on. So it's all built based on neural networks. So that's why this conference was already very popular. But at that time, it's 2017. There's nothing to do with ChatGPT. Okay, we didn't know that. And that friend, she's very active in academia. She didn't mention anything. She only told me that the top three, like the AI gurus, all came. Um, I forgot their names, but the guy from Facebook, one from Google, and then the other is Andrew Wen, right, from Stanford. Right now, Andrew Wen does his own thing, but they all came. Okay, so it's a very famous conference. But this paper was initially published here in 2017 in the NIPS conference. At that time, it wasn't really that big deal. So I think I look at some statistics in that year. I think they had maybe hundreds of papers accepted, a thousand papers submitted. They only accept hundreds of them. Okay, the very big one, but very, very tough to get accepted. And then they select some of the top papers, honor papers, the best papers. This paper was not among the honored papers or best papers at that time. Okay. But then later on, it turns out that this one to be really, really powerful because later on, pretty much all the GPT versions and then Google's project and all built based on this core idea. But obviously, OpenAI did a great job to turn this into a larger scale and then put that into practice. Okay, but then you need to know that the original idea or architecture behind all the language model, how we're training and building them, is coming from here. But obviously today, I think the structure they do is probably has been optimized a lot based on the initial version, but some of the key ideas is still coming from here. And then this paper also very special because the title, okay, the title is not a typical academic title, right? So if you think about the research paper, you probably seen that. They give you a very long technical title you cannot understand. So that's how the traditional paper looks like. And then they actually create this type of title. Honestly, today, this type of title is very popular. You often see that in a different conference. People like to follow the style to make it a little bit casual, more interesting. But you have to say that this title actually does do a good job. On capturing the key idea, okay, which is the idea about attention. So the paper was written mostly from Google, people from Google. All right, so you can see the 8 authors here. I don't know the last one. The last one should also be Google. I don't know why he put the Gmail here. But then they were all in the Google research. Oh, actually, sorry, not Google, but this guy from Toronto. Okay, Toronto is very strong in AI. One of the professors there, I think he left, join Google, right? And then so probably there's some kind of collaboration. But as you can see, the Google Brain was the team that's specifically working on AI stuff. Andrew Wynn was also in Google Brain, and some other people also works there, very famous ones. And the Google Research is their research and department that they don't work on the product, but they do all the different kind of algorithms. So Google has been very strong in algorithms and AIs. If you think about before ChatGPT, Google was leading a lot of things in terms of like a Google Assistant. A lot of the feature they do, they're pretty good. They have a lot of things. That's why I heard recently, I haven't used Gemini too much. I don't know if you guys use this a lot, but I heard that they're definitely getting a lot better. And recently, Google had this model called Nano Banana. I don't know if you heard about that one. It's an image generation model, very popular. This one. So this one happens recently. Okay, it's another like image generation model, just like Midjourney, ChatGPT then does the same thing. But from a lot of tests, and people found that this one is currently the best model to do the image recognition or image generation. And initially, this was a very secret project. People were trying to find out who actually built it, but very quickly, people from Google relieved that this is actually done from a Google team. So anyway, so it's Google team pretty strong on this one. That's why they're doing very well. They're capturing the trend. So very advantage. But from the paper, you can tell that why they're so leading. And the interesting part is that all of these authors today, I don't think they are at Google except probably one of them. I did a quick search here. I don't know if this is accurate. Okay, so the first author, currently the co-founder of Essential AI, that's kind of a startup, and this guy he goes back to the DeepMind only last year, and right now work on a Gemini. And then he also worked on the Essential AI, so they work together. And this one created his own startup called Inceptive AI. And this guy, Sakana AI, another startup. This is Cohere, another startup. This guy works for OpenAI, and this one is another startup. Okay, so now once you can see today, okay, so when you talk about AI today, all right, it's really all about getting the top people to work on it. This is why, you think about these people in Google, they should get a pretty good salary and back package and everything. And the reason they will leave is that the moment they decided to do the startup, they can get a lot of fundings very quickly. Just because in this specific field, one thing you should know is that if you want to work on AI itself, like model training stuff, as you can probably already feel, the complexity of all of this is beyond our normal like study ranges. Okay, if you talk about algorithms, okay, advanced algorithms, even like a dynamic program, right? So it's hard, but it takes some amount of time. You can still understand it completely. But when they go to the neural networks and training model like this, I don't think a normal person will be able to capture and understand. That's why if you want to build the next GPT, you want to improve those, you definitely require quite a lot of understanding about the research, about the technical things, and you gotta be someone very special. So I don't know if you guys saw some of the news recently. Meta actually hired some engineers, like the package goes over $100 million per year, something like this. Now obviously you don't know what's sure now, but that showed today, um, everyone knows that if you want to do AI, you gotta get the best people. Okay, so that's why all of this one very quickly they actually left Google and they do their own thing just because they have a lot more options, a better option. Because in Google you're basically just a team member here, but now you got hundreds of millions of funding, and then you do your own startup, and you can work on your own project and product. That's quite different. Okay, right. But this is actually really special. This one didn't happen before. 10, 15 years ago, people from the industry also published paper. And at that time, wasn't a big deal. Okay, a paper, most people don't even take it seriously. They often feel that the research paper is not very practical. And yeah, they're not gonna hire you or give you money to do a startup just because you do a paper. But things been changing. I just want you to know that this conference called NIPS, okay, this conference is a very big deal. And one day, if you can actually publish a paper here, you will be noticed. Okay, so people will actually look at here every year and then trying to find out the newest trend and stuff. And because of the conference topic on neural networks, that's directly related with the AI stuff, Transformer. Since Transformer was created here, so this is basically the most important conference. And recent year, I think the conference has a lot of people to attend. Okay, I think it probably like over 10,000 people to attend the conference. For conference, that's a very big and large scale. A lot of previous conferences I went to mostly like 700, 1,000. That's already a lot of people, but this one is way more crowded. Okay, that also brings another thing I want to mention today is that I kind of briefly mentioned that moving forward, I think going to grad school has its own values. Okay. Not like 10 years ago. When I went to grad school, to be honest, at that time I was in a PhD program. I applied to PhD. But my purpose was pretty simple because if you go to PhD program, you got a scholarship. You don't have to pay anything. The tuition is covered, you got a kind of assistantship. Okay. For PhD student, master student, normally you don't have that. Right. So I did a PhD not because I want to do research. It's just a good option for me. But I never regret because I think PhD gave me a lot of more experiences, research background, gave me more career choices. But today, I think the PhD is different because 10 years ago, think about if I go to grad school, I did a 5 years PhD, and then you guys graduate from bachelor, and then you straight go to work for Amazon, Google, or Facebook, right? 5 years later, I got my PhD degree, but 5 years later, you guys are going to be already senior developer. Your salary is way more higher, and you're leading the team. And I come back to Facebook, and I may not be able to compete with you even with a higher degree. So that was the problem before because the industry, the development depends on your experiences. It's not depending on your degree, right? We all know that. If you want to write good code, you got to just practice. That's why previously the advanced degree or master PhD doesn't matter too much. The work experience matter more if you want to just do more in the industry. But moving forward, I think the things have been changed dramatically because coding is still good, but you guys already know how good those AI tools are today. It's really good, right? So that's why you really don't need to be there to train for 5 years to write really good code. AI can already do probably better than you can and faster, right? And all the company, while they're trying to invest and then build their own AI model, do the AI application, then they will require this type of things. Okay, so they need people who could actually dig into the models, training, neural networks, all these complicated things most people cannot understand, and then to do it. But I'll tell you that all of these things, you can't really learn that from bachelors. Okay, these are mostly coming from research. Okay, you got to join a lab, work with a professor, and do your own research project, run experiments, and you do the publication. These are all the academic work. Okay, so that's why today, if you ask me opinion about going grad school, I think it's going to value more because we can't really predict what's going to happen. Maybe one day, really, the bachelor's, unless we fundamentally change a lot of our undergraduate curriculum, maybe it's just not that useful. Um, but if you want to go do the AI models, the PhD will be very needed. And also remember, PhD is more valuable. Master, again, you still cannot really handle this one just with a master because the master is just to take some courses. Where a PhD, you actually spend at least 3 years to do the independent research project, work with professors, and put to the publications. You go to a conference. That's a very different experience. So anyone, if you got some kind of a thoughts or think about going to grad school, I think right now the timing is pretty good. Okay, but at the same time, it's very difficult. If you want to go to the PhD related with AI, it's pretty difficult, very competitive. Okay, everyone trying to go there. A lot of this PhD students these days from the top schools, from Berkeley, from Stanford, from other schools, they got really good packages because there are not many talent who can handle AI like this. If you can get some good papers in some of the top conferences, do some project, or if you ever work with some of the famous professors, your future is going to be quite different. Okay, quite different. Um, 15 years ago when I graduated, at that time I told you that the for Amazon the salary for bachelor is 90,000, master is 95,000, and then PhD was 100,000. So like you got a 5,000 more. I was 15 years ago. At that time, Google appreciated PhD a little bit better. Google probably gave PhD 120 thousand for PhD, a little bit higher than Amazon, but that's it. But today, if you actually do top research in AI, I think your package can be just negotiated in the early days. It's going to be very, very, very different. Okay, so keep that in mind. Is that well, AI is going to replace a lot of basic things. I think the advanced work or who is going to build those AI, that's going to matter more. But obviously, only the small percent of people who can build this one. Because if you just look at this one, it's not something that everyone can understand that completely. Even if you understand it, not everyone can really implement it and implement it in a large scale. Okay, so yeah, just if you are actually interested in some of the more research stuff like this, okay, so spend some time to look into it, get yourself ready for grad school, because only in the grad school or PhD program you can probably get a chance to do this type of research and investigation. If you start to work in a company, pretty much you're going to be busy with all the development work, and diving into here won't be that feasible. All right. Anyway, so the paper is not very long. Okay, I suggest everyone just to give a shot. You don't have to understand everything. Okay, just try your best. You can always use ChatGPT to help you understand it. But here I just want to provide a very, very quick overview here that I just want to use an example. As you try to understand things, also my suggestion is go back to the Hello World example and try to understand how it works. Okay, I think ChatGPT can give you a lot of this example. This example also comes from ChatGPT, but I tried a lot of different things. Um, but here is that we give you the input sentence. Okay, I like apples. Okay, we're going to use this one to train the model to make a predictions. Um, what the transformer is trying to do here, the most important thing, remember that paper is about attention. Okay, it's almost the same idea that we human using human eyes to look at things. You look at something, you often have attention, right? You can't really see every single detail. There's no way you can do this. So that's exactly what I told you last time. A lot of algorithms, when they work well, if you can simulate how the real world works. Okay, because we figure out the previous like RN example. If you look at every single word in sequence one by one, and that's not going to work. Not only it's inefficient, but also you're going to lose a lot of important information. So you had to got to focus. That's the attention. Okay. But how do we implement the attention? It's all about how embedding things, how do you represent the thing, how do you analyze the final representation of the words and text information. All right. So you break them down into 3 different words. All right. And then what they're trying to do the encoding is this. So they want to generate some kind of vector. Okay, again, you can't use strings. You have to generate some kind of vector or numbers to represent it. But what the paper suggested was that for every word, the vector should cover these 3 aspects. They call it query, key, and value. Honestly, this part is very abstract to understand. You have to look at different examples. Okay, I'll only provide, once again, today I'll only give you a very, very shallow, brief impression. Okay, you can't expect I can explain this one. To be very honest, I can't explain this one, but try your best to understand what you're trying to do. But I want to tell you that they have designed a new way to embed the word into the it's almost like a vectorizer, right? So we showed you the count vector is very simple, but this one they use this kind of a QKV kind of model to vectorize it. The Q is kind of a query, so they want to analyze for that word, what is the thing that word is looking for? Okay, obviously that information is going to based on the type of the word. It's a verb, it's subject, it's object. So all of those, and also as this word, what can I offer to others who are looking for attentions or relationship, and also obviously the value. So the value is normally the word itself. So these are the actual things they're trying to capture. So this the value is very easy to understand, but also we want to capture what I need, what kind of information I need at this word, and also what the information I can offer as a word. Okay, so it's a really kind of a demanding relationship. So look at this word here. Okay, so I like apples. For the query is that, who is the subject? Okay, that's the question I want to know. Since I it's just I, so who is the real subject, right? And then the information I need is I can offer. Okay, it says I can be the subject. Okay, and the value will be the I itself. And like is a verb. Okay, so as a verb, I need to understand who likes what. Okay, these are the questions. And then the things I can offer is that I can provide that verb or the action. Okay, and then the value is this. So that's how they're doing the analysis for that words. But this is the final results. Okay, in order to get this table, well, you have to do another natural language processing. You got to figure out the verb, all the different types, the relationship. You scan all the words, and then you form this kind of embedding. Because once you have this one, once again, you turn all the words into a very organized, cleaned format, right? So kind of like vectors. Then you can run all the machine learning, the training process. Okay, so when you're trying to understand the transformers, the first thing you got to understand is the Q key V. Okay, I'll leave that one to yourself because I don't think this is something I can use a couple slides to show you. Even this slide, I think that's still very confusing to most of you if it's the first time you see this. But at least know the high level ideas first. All right. The good thing about once you figure out the Q and the K is that because the Q and K obviously that's the question you're looking for information and K is the ones you can offer, right? Then you can do some matches. Okay, you can look at other words, you can see how the other answer is gonna fit your question very well, and that's how you can build some kind of relationship, right? So like this word need to find out the subject and also the object. So they look at the word I, that's which is the subject, right? So that actually fit this question very well. And same time, the apple also fit the question like very well. So because you already defined those somehow, and all we need to do is this kind of matching. Okay, I might look for a verb. That's why. So this like word could be working very well, and Apple needs to also look at word verb, and then they actually build that relationship. So it's very simple. Okay, it's just once you analyze the type, the question, and the things you can offer, then you can match them together. Okay, once you know that, you just collect the values because the value has already been stored there. Just provide that value. Um, and then finally, you will have this kind of generating the final embedding. The embedding will be showing as numbers, okay? But what the embedding is going to tell you is that every word now, when you save it, you save not only the value but also kind of the relationship between others based on the matching result you got, which is here like it's a can be used for the subject like, okay? This one was subject I and object apples based on all this analysis. So finally, you could actually form this kind of relationship. All right. This is the kind of attention graph, right? So you can see I is connect with the apple, and then like also connect with apple, and how much the weight, obviously, you can give a weight based on, if it's a very complicated sentences, a lot of words going on, then you can probably give different weights. But that's more deeper like algorithms. Okay, we're just want to show you the results. Okay, so after all this analysis, you have to show for every word how strong that attention is to the other words. Okay, so it's almost like a relationship. Okay, the weight. Okay, for this word, which other words matters more. So that's what they're trying to capture here. This is coming from another example, just give you more specific idea, right? So eventually, okay, you give a sentence, you provide all those words. Every word will be represented by a vector, and that vector can be very, very long. Okay, so not necessarily just four, can be many, many different dimensions, but it's trying to answer all these questions for you. Okay, and also trying to match that with all the other like attentions. Okay, so like this one here probably tells you about the tension between the first words and all the other words, and also including the self. Obviously, the word to itself, if you look at the diagonal, that one has a very high level value because obviously that matters. Just every word is a matter to itself. Okay, so but this is just a kind of very concrete representation on what this encoding is trying to do, which is the most important part about the transformer. Because if you understand this, then you can think about as you train a model, then all the attention, this value are going to matter. Okay. Um, yeah, like if you have a lot of this one stored, right? As you do the prediction, that start to make more sense. Whenever you see a word like a like, right? And then you're gonna find out what's next. And then based on a lot of information, and something like this probably will pop up. Okay, this also explains the inference because the language model isn't just showing you the things they have seen. They can show you the things that they haven't seen because, for example, I like Apple, or you can say that I'm a guy. Guys also most likely likes watermelon, right? So next time you can probably do I like watermelon. So if you determine that I is a boy, right? So something like this, you can see this kind of information will allows you to build that kind of inference relationship, right? So that's why um, once you have a skill that's large enough, it will be able to capture so much information. But that part, again, even today, scientists cannot really understand how the build model works. You can only, you know, abstract it into different layers, but in terms of how exactly the code works, that's the part that beyond our imagination. Okay. So for the first step for the transformer, okay, all I need is everyone try to understand this encoding, okay, understand what is attention, okay, how do you calculate attention? Very high level idea. You don't have to even do the code. I can't even show you the code. I can generate the code, but running the code doesn't make any sense. Okay, so it's a pretty complicated process. All right. My suggestion is that after today, read the paper first. Okay, get this paper. This is not a very long paper, as you can see, only 7, 8, 9 pages, a single column. Yeah, 9 pages. And then yeah, look, just see whatever you can understand. You can ignore some of the formula stuff, focus on the graphs. But this one talks not just about encoding, but also the whole architecture. What's the input and output? And then you can always use throw the paper to ChatGPT to help you to understand it. You can bring different examples until you got a better understanding. Okay, so yeah, so here I just want to, but then the difference is that I think the important part again today is that also understand why the sequential model isn't good. Like especially this image here is actually very important. Okay, this obviously is not the most optimized way to process the text. Okay, so now think about the transformer model. All you need is to provide that whole sentence because everything I can find out the direct relationship, and then you can skip all the things, look at this one by one. Um, yeah, but once again, that's a very high level idea. Okay, it's still very hard to completely visualize and concrete it. Yeah, but anyway, so these things are very new. Okay, as you can see, the paper was only published in 2017, 7, 8 years ago. Very new stuff. Okay, so there's no one called like expert. So AI was here only for 3, 4 years, generative AI. So it's never late to pick up some of the things like this to learn it. You don't need to have many years like experience. Most people in computer science field in the industry never done this before. So it's never late to try to research and learn something. Okay. All right. Yeah. So today, yeah, that's the goal for today. I just want to give a quick like an overview, very high level overview. Okay. You should still feel very confused. I don't think you will understand the whole thing, but remember what I showed you today. Some things I feel important. Then bring those to look at some of the papers and yeah, try to get more things out of it. All right. Okay, yeah. I just want to stop here. Just give a quick introduction. We're not going to be able to dig into the algorithms too much more, but I want to bring some of the open source models, see if we can run those next week, just to do something a little bit more practical. All right. Sounds good. Any questions? All right. Yeah, and as I mentioned, spend some time, look at the paper, it's a very classical word to learn. Okay, so I will see you guys next week.